Okay, so there was a question in class on why the depth of binary tree is to be log n or theta of log n, right? If you have n nodes in the binary tree. So let's try to prove this by induction. So if you have a binary tree of level 1 or depth 1, so you have a root node and you have two children for that root node, right? So the number of leaf nodes at depth 1 is going to be 2 to the 1, 2 raised to 1, which is 2. Okay, so now we are looking at complete binary trees, so each node has two children. All right, so for binary tree of depth 1, the number of leaf nodes at depth 1 is going to be 2 to the power 1, right? This guy has two children, that's what it is. Now the hypothesis is let the number of leaf nodes at depth d minus 1 be 2 raised to d minus 1. So let's take up this binary tree. So you have each node having two children, okay, and so on. So this has two children, and this has two children, this has two children, and so on. So at depth d minus 1, which is this, let the number of leaf nodes be 2 raised to d minus 1. So what we have to find is the number of leaf nodes at depth d. Now you see at depth from d minus 1 to d, each leaf node or each node here actually has two children, right? So the number of leaf nodes that are at depth d would be what? Twice the number of nodes at depth d minus 1. So if the binary tree stopped at depth d minus 1, these would have been your leaf nodes. But now you have each of these nodes, that's why I put the leaf nodes in bracket, each of these nodes have two children. So the number of leaf nodes at depth d would be the number of twice the number of leaf nodes at depth d minus 1. So each of this has two children. So the number of nodes at depth d would be twice the number of nodes at depth d minus 1. That's what I have here. Okay. So if this leaf nodes is a misnomer, then you can even remove that term over here, right? All right. So which means the number of nodes at depth d minus 1 is 2 raised to d minus 1. So twice 2 times that is 2 times 2 raised to d minus 1. So that is 2 raised to d. So now we have the number of nodes at depth d is 2 raised to d. So if you want to count the total number of nodes in a binary tree, it would be 1 plus 2 plus 4 plus so on up to 2 raised to d. So that is your n. Okay, so this is n equals, okay, so what is the formula? We saw that in the first chapter. If you have 1 plus 2 square plus 2 cube plus so on up to 2 raised to d, that is 2 raised to d plus 1 minus 1. This minus 1 is not an exponent, it's just in the regular form. So 2 raised to d plus 1, then minus 1, the whole thing divided by 2 minus 1, and 2 minus 1 is 1. So this is simply 2 raised to d plus 1 minus 1. So now take this negative 1 to the other side, so it's n plus 1 equals 2 raised to d plus 1. Now take the logarithm on both sides. We have, this is actually a lowercase d, so alright, so d plus 1 equals log n plus 1 to the base 2. So that's what happens if you take the logarithm, right? N equals 2 to the x, so x equals log n to the base 2. So here d plus 1 is exponent equals log n plus 1 to the base 2. So d equals log of n plus 1 to the base 2 minus 1. So log of n plus 1 to the base 2 is theta of log n, and we have just negative 1, so you can write the whole thing is theta of log n, right? So that's why the depth of a binary tree of n nodes is theta of log n. Okay,